Let me get started, and I'm going to introduce myself. This talk is going to be about Compute Link Express. So, it's actually going to talk about the latest announcement about the Compute Link Express version 3.0. And I am Narasimha Babu GVL. My long name is Babu, my short name is Gundavarapu Venkata Lakshmi Narasimha Babu. And so, then from which area I'm coming from. I'm working as a synopsis scientist. I hold a master's in digital systems and computer electronics from JNTU Hyderabad and a BTech from NIT Warangal. And with the background and expertise on the standard protocols, digital communications, embedded systems, right now my focus is to be able to drive the architecture for the protocol-based verification IP solutions and also for the hardware verification for protocols. So with this, I'm going to go into Compute Link Express. The Compute Link Express is a standard which is actually driven by CXL Consortium. I'm going to actually represent CXL Consortium here and do a overview session of the Compute Link Express standard. So when you look at in terms of what we're going to do is, I'm going to talk about just a CXL overview, and I'm going to talk about the CXL representative use cases and touch upon the features that are coming in CXL 3.0. So we have seen that a lot of discussions and then inputs that have been given during the day that the compute is actually having the ability to scale up and the needs for having high speed compute is growing. So as the compute is growing, the memory also needs to catch up in order to be able to provide a low latency communication between the compute and memory such a way that we are able to achieve what the industry needs are. So considering that entire so considering that what exactly is the CXL is all about, we'll talk. So I just talked about the CXL Consortium, and if you look at there are companies who are part and act as the board of directors for CXL. So the group, if you see, the companies which are involved with data processing, involved with compute, involved with the companies like Microsoft, where they are developing the complete applications. So there's actually a lot of companies came together to define the standard, and plus what we saw was the number of member companies who are actually part of the CXL has grown significantly. It's about grown to 200 plus companies, and we see that a lot of active participation and contribution to the standard. And if you look at the landscape, because all these has been talked from the morning, one is proliferation of cloud computing, and then we have this growth and AI analytics, and we have the cloudification of network and edge, and we heard a lot about it. And in order to see what it is that CXL is trying to do, the first and foremost is actually it's acting as a interconnect between the CPU and the memory and the accelerator. One key aspect that CXL does is that it's built on the PCIe infrastructure. That means the physical layer of PCIe, the electricals, if you look at it as a PCIe system or a Compute Link Express, they are compatible. And not only that, it's actually also leverages the ecosystem that's there from the software standpoint to be able to easily discover and identify the CXL devices to take the advantage of the presence of those. The thing is here, if you look at the landscape, there are applications which are not necessarily being done by CPU, but it's done by the chips which are physically located outside of CPU. So the main focus in the past has been that if you talk about a coherency and then you have a host of compute elements, the requirement is to be able to maintain the coherency within these cores which is there, and the cache coherency is actually focused on around the compute. Now with the key functionality moving outside, and that also present the physically located chips, it's becoming key that we should be able to maintain coherency between the two physically located chips. So one is this being able to take the coherency between two systems is actually becoming a key, and now if you need to maintain the coherency, the important aspect is the latency has to be considered. Otherwise, the meaningful whatever functionality you wanted to achieve, you may not be able to achieve. So that's one thing which actually, if you look at in terms of maintaining the coherency, and then also if you see that I should be able to use the sharing of the memory or pooling of the memory or being able to disintegrate the memory and be able to use it effectively is becoming important. So it comes to the standard. We'll talk more about this CXL 3.0, what is about 2.0 and other things. And if you look at what are the representative CXL use cases. So you have compute, which is the processor and the associated memory. It's a type 1 system, which actually is talking to a device, which is an accelerator. It can be a NIC, or it can be NIC atomics, or it can be that such a system where it is important to have a coherency maintained between these two systems. So that's just about the coherency between these two systems. And then if you look at the last one, which is a type 3 system, here what we are looking at is the memory needs are huge in the overall system, and directly connecting such a huge memory requirement to the processor may not be feasible, and because of these amounts of memory that is needed. And so the whole thing actually acts as a memory expander to the CPU, where this can be used for either expansion, or you can basically have different types of technologies. That's about a type 3. And there is a type 2 system which actually has both. It maintains coherency between the processor and the device, as well as able to provide a memory expansion capability. So these are the typical representative use cases. And now given these use cases, in terms of how these CXL systems can be built, is an interesting aspect which we'll look into. So I'm actually told I'll come back to this with respect to what's happening at the CXL Consortium. The first and foremost is the specification got released in March 2019, and that's the first version of the spec. And immediately the moment the specification got released, the consortium got announced, we saw there's a lot of traction in the industry on this protocol. Then in September 2019, the actual consortium got officially incorporated, and then the next version of the specification that been announced. And after that, actually there's an aggressive pace at which the specification updates are happening, and now there was a 2.0 version of the specification that got announced with enhanced capabilities, and about 2 years from there now we have a 3.0 specification that got announced. One of the biggest aspects here is the 3.0 specification that is announced is backward compatible with 2.0 and backward compatible with 1.1. So the 3.0 announcement happened early August, And if you look at the key aspects what 3.0 introduces into the specification, one is about the fabric capabilities. The second one is about the improved capability, and this one for better scalability and resource utilization. We'll talk about it, how it's actually helping that significantly. The third one is the bandwidth itself at the physical layer gets doubled. The reason for the bandwidth getting doubled is it continues to use the PCI Express as the electrical, and it actually is based on the PCI Express 6.0 specification, which actually uses 64 gigatransfers per second with the PAM modeling. And although the bandwidth has doubled, the latency that got introduced because of the change in the bandwidth is almost similar to what it was there with 2.0. That's the biggest advantage. And amount of throughput you get on a CXL system with 16 lanes and 64 gigatransfers is going to be huge. And one key aspect is the CXL has two paths. As we saw in the previous picture, there is something called a CXL.io, which is mentioned everywhere. That is actually being able to run the PCIe workloads in order to be able to discover the system and then to be able to continue to use PCIe functionality in a CXL, in addition to specific aspects that are required for the cache and memory. Continuing on to that, if you look at the specification, as we talked about all this, the fabric capabilities and management, improved memory sharing, enhanced coherency peer-to-peer, we will actually go and look at each one of them in detail. So if you see, the key here is, if you look at the thing, is basically multi-headed devices, multiple type 1 and type 2. And these two aspects are from a single domain. The whole, if you look at a system perspective, it's actually scaling to provide ability to be able to go to multi-domain. And that is one thing. And in the previous versions, you may have a restriction in terms of how many devices I can have below a switch. That restriction is also getting removed, which is actually going to make the whole ecosystem very, very attractive. So this is just a comprehensive list of items, and you look at the different versions of the CXL standard, starting from CXL 1.1 to 2.0 to 3.0. We'll talk about the key aspects actually, key aspects, which is about, if you see here, the memory pooling, the global persistent flex, flash ID and switching. So the 2.0 actually introduced the CXL switching. And as we are going to see how the security aspect is becoming key factor now, considering that in India, we have about 600 billion transactions, digital transactions that are happening, which is a huge number, and it is becoming important that the security is the key. So CXL, what it did is it introduced what is called as an IDE, which is a integrity and data encryption, which is actually going to help to use it as a basis for building the security at the overall system environment. And the memory pooling, the first generation had a single logical device, whereas the CXL 2.0 has an ability to have multiple logical devices sharing the memory, where whatever CXL system has, it can actually take the memory and allot it to different host domains. So then it came actually the CXL 3.0, which we talked about. And in order to enable all this, there may be something that we should be able to have an ability to transport the packets effectively. So what happened is they introduced a concept called as a 256 byte flit mode. So when we say about 256 byte flit mode, the CXL 1.1 and 2.0 had only 68 bytes, where you can send as a atomic packet to the other side of the link, whereas the CXL 3.0 introduced this 256 byte fit mode, which is actually going to be useful for the additional functionality that has been defined. So the reason why is that it needed additional fields that are needed in order to accommodate the information that is needed to be able to use it for effectively to support the additional features which are listed. So moving on to do a recap, I'll just talk about what's all about CXL 2.0, the memory pooling. So as I said, the CXL 2.0 introduced a switch. So that means I can have multiple hosts connecting to the CXL switch and multiple devices connecting to the switch. And now we have a PCIe switch where actually PCIe switch can have multiple levels of hierarchy. We can come back to that. Whereas the CXL switch initially introduced in 2.0 had only one level where it could have multiple hosts. And now if you see the memory, whatever is there from the device perspective can be allotted to multiple hosts. So this actually what happens is based on the application workload, depending on the needs, you can actually have a finer grain memory allocation. So which is actually very attractive. And then actually if you see with respect to the switching, it only supports one level as we talked about it. And when it comes to the CXL 3.0, it actually made an interesting change. One thing is you can have either a cascade of a switch or you can basically have multiple switch levels. That means I can fundamentally have an hierarchy, and plus it's not only this, there's much more to it. Let's see what happens. So now what happens is it helps a fan out. So if you see here we have a switch, we have so many devices connected, and they have another one which is connecting more number of devices with two switches, and we have three switches here, and then this could be again can be leveraged in the way how we want to design the system. So other one is actually if you see many of the times if we have multiple devices, and we know this concept even in PCI Express where a peer-to-peer communication was effective. It is not required for me to go to the host and come back. If you can enable a peer-to-peer communication, that is actually going to be advantageous. And then so the CXL 3.0, it enables the peer-to-peer communication within the hierarchy of the devices. So this, whatever it is there, the virtual hierarchies are the association that device maintains a coherency domain. That's very important. It's not peer-to-peer communication, but also there is a virtual hierarchy which says this is one coherency domain, and it can have multiple virtual hierarchies in the CXL system. And then when it comes to the aspect where when you have actually enhanced the switching capability, there is also one more thing which got enhanced is about the memory sharing. So now what happens is a device memory can be shared to all the hosts. So if suppose there is a device memory, there are multiple hosts through the switches, you can actually share the memory, and the hosts can have coherent copy of the shared region. That means there is a memory here which is shared, and the host can have coherency between the two different hosts. This coherency can be maintained. That's actually a big advantage. When we say that I have multiple hosts and I have a device and there is a memory region, I can actually maintain the coherency between all these, and with the latency that is required for my system design. That's a big advantage where it can actually use this feature to be able to scale the application needs. And one advantage basically is that it has defined the mechanisms to enforce the hardware coherency. So ultimately if you see that if in order to maintain this coherency, and if everything has to be done in software in order to maintain this coherency, it could become a large overhead. and it has defined the mechanism to be able to do it and enforce this coherency in the hardware itself. So that's actually a big advantage. And we saw about memory pooling, which was defined in CXL 2.0 itself. And now we saw that CXL 3.0 has defined memory sharing. And here it's possible to use both combinations together. That means I can have the shared copy between multiple hosts as well as you do the overall pooling. And the CXL Fabric Manager is the component which has the visibility about the overall system, and it knows how to actually sustain, means deploy, and then say that this is how the logical devices are going to be, this is how it's going to get connected, and all, get the whole setup up. And that later, if I need to basically change and say that I need to move a particular device out and then bring in a new device to define a new set of memory pooling requirements, you can actually use the hot plug feature, which is available in the PCI Express, to remove the device and plug it back again, reconfigure the system to redefine the thing. That's the biggest advantage, is that when the system is operational, you are actually able to dynamically change the configuration as per the needs. And maybe that's what actually could be one of the aspects which might help to achieve the memory disintegration that is needed. If I have a memory and then I know some of the systems are not using, I want to configure the entire thing, it's possible to accomplish through that. And this is another one which, if you look at in terms of the CXL 2.0, what CXL 2.0 defined was that you could actually have a switch and you can only have only one of the devices as type 1 or type 3 to the leaf node. And then it is possible to maintain the coherency between this device and the compute, and there's only one device. The reason because is the switch does not have anything that it's going to decode in order to route the packets in CXL 2.0. So then all other devices are type 3, which are kind of memory expanders in CXL 2.0. But in CXL 3.0, what has happened is now each host root port can connect to more than one or multiple type 1, type 2 devices. That means when all of these devices which are actually having coherency, having memory management, needs to be maintained, this entire system and the semantics that are defined can actually achieve the coherency in this environment, and which is actually, if you see, having several of these devices and being capable of actually doing the coherency between multiple devices within a single hierarchy. This I can take it as a single hierarchy, then I can have multiple hierarchies. And now is it possible for me to achieve coherency across multiple hierarchies is another one which comes to us, and we will see whether it is really possible with what is defined in CXL 3.0. And one of the key aspects, if you look at the CXL specification, right, the coherency aspect is actually asymmetric. What it means is the host side, whatever that is needed in order to be able to maintain the coherency, most of the functionality is in the host. What device does is it does execute or does only bare minimum aspects functionality that is required in order to maintain the coherency. So in that way, one thing which I see is the biggest going to be advantage is that when you design CXL devices, the complexity of the device in order to maintain coherency is going to be much lesser, because it just does what it is required. And so in that way, it could be more efficient in terms of the overall design, and it could become very attractive. So now that takes us to as actually we talked about the memory sharing, we talked about memory pooling, we talked about the switches where it could be cascaded, where it could have multiple levels of hierarchy. And now let's actually go to the next one, which is about fabric. So what is this fabric? So one thing what has been done in CXL is there is a definition called port-based routing where the source address and destination addresses are defined in the packets you transfer. And so now the switch has ability to see what is the source where the packet is originating and what is the destination it needs to route to. And that means effectively I can go and connect these switches in whatever fashion I want. So as the source ID and destination ID are 12 bits, it means that we would have almost 4096 devices where you could be doing a cross routing that is possible in the system. So if you see the other interesting aspect here is the switch is connecting to these nodes. Now in this fabric, the nodes can be either a CXL host, or I can be a CXL device, or I can even have a usual PCIe device. So now I have a PCIe ecosystem. I want to actually go and scale to be able to make it and take the advantage of the CXL coherency and the memory management capabilities it is bringing in. If I need to be able to go and do that, I can actually go and build, instead of starting from scratch, build it from the systems that are existing today and scale it up. That's one of the biggest advantages I see. So if you look at the one specific example, as I said, the nodes can be host. So that's why you see here, this can be a host, this can be a host, this can be a host, or it can be type 1 device, or it can be a type 2, or it can be a type 3. And if you look at the ecosystem from a software standpoint, any PCIe system, when you go and look at it, when the system comes up, there is an enumeration. So the PCIe, when it does an enumeration, it will go and figure out saying that it's a PCIe device, the hierarchy and whatever it is, and discovers it. So the way the specification has done is going hand in hand with PCI Express. In the PCI Express configuration, you define the capability that I am a CXL device. The moment it discovers it's a CXL device, then the discovery of the CXL device itself to starts, and then actually it goes and discovers the capability of the CXL device. So it's actually very well architected in the sense, if you see the PCIe, how it moved in the standard. From 3.0 to 4.0, it took maybe 6-7 years. From 4.0 onwards, the PCIe as a standard is changing its generation every 2 years. 4.0 to 5.0, 5.0 to 6.0. So when you look at 4.0, what it has done is it did a lot of groundwork in terms of the technologies that are needed. One of them is the RX margining. That means whatever is the physical layer, software actually goes and iteratively finds out the best sampling points for me to get the minimum, the best bit error rate. And then actually it went and defined the scaled flow control, where it increased the number of tags to 728 tags or so. So actually there is a lot of groundwork that has been done in PC Gen 4, which has established itself as a very strong technology to scale up. And then it actually came Gen 5. The entire focus has been on the physical layer for the Gen 5. And one very biggest advantage that is there in Gen 5 is when the system is linking up, it can communicate and say that I would like to negotiate to run an alternate protocol. And it can exchange the parameters for the alternate protocol, and then it can actually go and work as a completely different system within the PCIe framework. Or I can negotiate and say that I'm going to continue to be in PCIe only. So That is one thing which has been taken and used in order to be able to say that I am going to negotiate initially to say that I am a CXL system. And from that negotiation, once it's a CXL system, it actually goes and discovers, and the framing, whatever the physical layer framing, what packets it's going to transmit, all of them are going to change. But the smart thing that has been done is I can actually send whatever is needed from a CXL standpoint, which is for the cache and memory, as well as multiplex whatever I need from a PCIe standpoint, which is CXL IO, and can send on the same link. As long as we can actually take and design a system where I negotiate and then I fall back and say I'm only PCIe, then this whole system will still work as PCIe for that particular node. And then you negotiate as CXL, depending on the discovery, it can work as a CXL. And so now it actually allows your heterogeneous integration of the PCIe and the CXL system very easily. So looking at that, now if you look at in terms of the fabric, what it can actually help. One of them is actually a fabric attached, global fabric attached memory. So if you see, there is a memory which can be any technology. You could use NVM, it could use the DRAM technology, and then you could actually have a CPU directly connecting, because it could be just a CXL expander, so I can connect it through the CXL, or in whichever way it needs, or I can connect it through a switch, and fundamentally, and so what I can actually is the biggest advantage is that you can do the disaggregating the memory from the processing unit, which is implemented as a large storage pool, especially when you are doing cloud services, and then there is a huge memory that's available, and memory not getting used in a cloud could mean a cost to the system. And then if actually needed to be able to go manage this whole thing, this could actually provide an effective way. One key aspect, if you look at the CXL, is that we had a protocol called as Gen Z, which was actually driven by AMD and others. The Gen Z actually got merged with CXL, which actually means that the assets of Gen Z is now into the CXL Consortium, and Gen Z actually defined pretty good aspects with respect to the fabrics, and those things are also getting defined into CXL. And if you also see the latest announcement, the CXL has entered an MOU with the JEDEC, which means for whatever memory specifications the JEDEC is defining, there's going to be a good amount of interaction between these two organizations, which is actually going to benefit as we actually move along to be able to cater to the needs which initially talked to that. There is a compute which is growing in terms of the speed at which it can work. It is actually applications are asking for the memory needs, and to be able to build a system which can meet all these requirements. That actually seems to be a promise, because the CXL is now moving towards taking care of all this from a system perspective. So there's another use case. So if you look at in terms of, actually I talked about this, you could have multiple media types like DRAM or flash or any future memory types. And if you see here, there is a CXL switch, and we have this global FAM, and there is a machine learning accelerator and the global FAM device in the fabric architecture. And so now using, if you see, this is one of the interesting aspect where this could be one of the use cases in which we would be able to take the advantage of the capabilities that are defined in the specification to be able to build first the hardware level for this, as well as to be able to manage with the software what you intend to do with this. The next one is again another example is in terms of high performance computing and analytics. So again, we have a host connecting to the accelerator, and there is a switch. you need the sharing memory and networking devices to reduce the cost and improve of the overall efficiency. So again, the semantics that have been defined today actually can enable to implement such a system. So if you look at in terms of the other use cases, so now we have different racks. If you look at, we have different lags. You have different racks, and if you basically see that there could be a NIC, there could be a CPU, there could be switch accelerator, there can be switch memory, and if actually wants to communicate from one rack to another rack, and using this CXL switch concept, using the concept of the fabrics and using the port-based routing, it basically helps to scale not only at the board level but also at the rack level. So this actually makes it, if you see from the place where it started in 2019, where the intent was to be able to enable coherency between two physically located devices, to 2020 where it actually added memory pooling and the switching capabilities in CXL 2.0, and both 1.1 and 2.0 took the advantage of the PCI Express 5.0 capabilities like 32 giga transfers per second and the alternate protocol negotiation, and plus continue to leverage the PCIe configuration space aspects. And then came to 3.0, it significantly scaled with respect to its switching capabilities, with respect to the memory pooling, resource sharing, and then ability to have multiple types, multiple type 1 or type 2 devices under a switch, and then ability to have these fabrics where if you look at and think about in terms of how we actually can build such a systems that are actually going to scale for requiring the needs what we saw initially with respect to either AI or with respect to the network cloudification and edge. Those, it all seems to be slowly coming into the place, and at least I see that this is what the industry wanted. And actually on top of this, if you see, there is something more that is getting defined. It's more at a software level. We have this virtual machine environments today, and they manage by means of the virtual machine manager to be able to create a complete system that can be for one specific user or whichever. There are security aspects that are getting defined on top of the CXL specification as well as PCI Express, where you can create this trusted virtual environments, which actually means that it has a lot more security in the using the software as well as the hardware aspect, such a way that it is actually going to give a lot of confidence to the users or the application implementers to be able to say that my system is going to be secure, because the threat that we are seeing that the systems can be hacked is continuously growing. And then the next topic is going to be on how the hardware itself is going to take care of the security, is going to be talked about that. So to a summary in terms of, we talked about whatever the CXL 3.0 features, and it is about the enabling new usage models. And now actually if you see, if you go to the Compute Link Express, you can actually download the specification and you can get an eval copy. And the best would be to be able to join the CXL Consortium, and you can see that the amount of topics that are getting discussed, and then to define the specification, and the amount of participation from the industry is amazing. And so you can have an opportunity to make a difference and a change. So thank you. And any questions? Yes, please. So Mike. just.
Yeah, still go back. Yes. So here device 1 and device 2 is like let's consider DRAM.
Sorry, could you repeat?
D1, D2, D3, D4, or let's consider that is a like DDR5 DRAM as a device.
I assume, okay, through the CXL, it is talking to a memory, yeah.
No, the upfort is the host device, right? But if you see this device which is connected to the switches, correct? So who will initiate the transaction between the peer-to-peer?
Okay, good question. So who will initiate the transaction between peer-to-peer? First and foremost is somebody needs to have a system view,
Yeah.
right? In terms of the address space. So ultimately, if you see the address space is all clear. So now, from the initially, if you look at the way the entire thing is, the system gets discovered. So this H1, H2, H3, H4 and all this is part of the CXL, we can say as root complex. And when the operating system comes to know saying that this is in the CXL domain, for which there is a switch and then these devices are there, this is how the address map is there. So now once the address map is there, each one of these devices, they know what the address map is. Once suppose a communication is happening from peer to peer, it needs to access something with another device and it gets generated. The switch has to look into saying that it belongs to this and it's a peer-to-peer communication. It actually does the routing. So while doing that, it has rules it has to follow. It can't just send it across. And whatever responses that comes, again, it has to be taken. Predominantly, it is something similar to PCI Express. And then it also leverages something what PCI Express has as a framework in order to be able to achieve this.
Yeah, I agree. Suppose if host initiates, device can respond or he can return back the data. But here, what you are trying to say, device is like any host we can consider or like some slave devices which can support?
Sorry, could you repeat?
I mean, I just need to know in this diagram, D1 to D6, is this any host sits there or just like a slave devices, like supporting or some devices?
No, it would be all based on, see, initially when I want to access, there is a semantic which a packet gets sent. And this is the address for which I'm going to access and additional fields there, saying that this is going to be peer-to-peer. The moment that is interpreted, the router knows where to route it. The moment the response comes, the router knows where to route it back. So that's how it works at the top level.
I agree. Between host to multiple devices or between multiple hosts to between multiple devices, host can initiate to any topology and he can get it.
Yeah, that's
but in this, like all our devices, right, how he will initiate? That's my question.
See, if you see in CXL, the request can come from device or it can come from host.
It's not a slave.
Both.
It's not a slave.
Both sides.
If it is not endpoint, then it is okay.
It's not an endpoint. Basically, even in endpoint in PCIe, I can initiate a memory request.
Okay. Yeah.
Okay. Similarly here, whether on a type 1, type 2 or type 3, I can initiate requests.
Yeah, I got it.
No,
Thank you.
sorry.
So does this take care of all the memory ordering, memory consistency issues are handled in this?
Yes, the specification defines all that. For example, if you take cache coherency, there are ordering rules that are defined, and it has to have those ordering rules. There are aspects with respect to the atomics, how the entire cache coherency is maintained. It's all defined as a semantics in the CXL transaction layer specification. It's very well defined.
And it also still software also needs to do additional stuff in this case, right? Because if it is memory coherency spread across, then
Yeah, software also plays a key role.
like the NUMA and stuff like that, right?
Pardon?
Like a NUMA and things like that. I mean,
Yeah. It actually, if you see, there is a CADT specification, which actually defines in terms of how the CXL device is discovered, how the information is passed on. There are different levels, right? The system is coming up, the firmware is going to talk and then bring it up. Then once it is there, it goes to the OS. Once it goes, then it goes to the actual software to manage the whole thing. That entire thing is getting defined, and each, like for example, the memory management subsystem team is defining certain things. There are whatever this software related things, this is getting defined. There are multiple groups which are working to ensure that the entire ecosystem is going to play well together. Okay, last question.
Last question. The switches, sorry, last one. The switches, what you are showing, right? I mean, do we really have those products today, or is
No,
it all
it is
theory
still,
right now?
it's basically what we are seeing is there seems to be interest where the industry is now starting to define switches, and we believe these products soon in the market. So last question, please.
Yeah, sir. So how is the industry readiness in terms of adoption? That is one part. And even the processes, are they already in place? Do they comply to the standards? Because the standard itself has been around for 3+ years now, right? So two parts to the question. Is the industry ready to supply the required processes and memory? Of course, I think DDR5 is good enough for now. The second part of the question is there any early adoption? Are there solutions already available as of now in the earlier CXL specs?
So that, if I understand the question correct, the parts are available and what is the early adoption and all. So two parts here. One is, if you look at from a hardware standpoint, there is interoperability testing going on between the host as well as the CXL devices. So I believe Intel seem to be having boards with both PCIe and CXL capability, which is the motherboards that can actually enable to build the ecosystem with the devices. Right now what we see is predominantly we are working with the semiconductor companies who are doing CXL designs and doing the functional verification or verification in a hardware on an emulation platform. So the lot of interest and lot of companies are designing the CXL based systems, and we expect that the actual designs that are the products will become available soon. What I understand is CXL based memory expanders have been announced by a couple of customers, especially the Type 3. Initially we saw a lot of interest with Type 3, and now we are seeing interest with Type 1 and Type 2. Okay, thanks, thank you very much. And now